Welcome to Ask and Learn.
Heated until its pressure doubles, and we wish to calculate the volume of the tank and the amount of heat transfer. We assume that air is an ideal gas, the kinetic and potential energy changes are negligible, and we can write the gas constant of air from our tables. R is 0.3704, and this is psi absolute cubic foot per pound mass R. So for part A, we wish to calculate the volume of the tank. Now we know that V is simply mR T1 over P1, where T1 is the temperature of state 1 and P1 is its pressure. Now these values are all known. So if we substitute them in, we get this to be 10 pounds times R, which is, as above, 0.3704, and that's psi cubic feet per pound mass R times T1. So the initial temperature is 525 R. And this is all over the pressure of the system in state 1, which is 30 psi absolute. And so we get the volume of the tank, V, to be 64.8 cubic feet. Now for part B, we want to calculate the internal energy of the system. So, or the heat energy, the heat transfer in the system. So we take the air in the tank as our system, and we write our energy balance equation, E in minus E out, our energy in minus our energy out, must equal to the change in energy of our system. And all we have into the system is heat. So heat transfer Q is in, and this results in a change in internal energy delta U. Remember, potential and kinetic energies are zero here. So we can write this as the mass of the system, the mass of the air, into the change in specific internal energies, U2 minus U1. And we can go one further and write this as M times the specific heat capacity for air at a constant volume, CV, into the change in temperature, T2 minus T1. So to calculate the final temperature of the air, we use the ideal gas relation, P1 V over T1, since V is staying constant, is equal to P2V over T2. So if we rearrange this, we can find T2, and T2 is the ratio of the pressures P2 over P1 times T1. And this is equal to 2, since the pressure doubles, times T1, which is 525 R. And so we get T2 to be 1050 R. So we have the final temperature of the air. Now the internal energies, U1 is equal to U from our tables at 525 R is 89.48 kilojoules per kg. For the final state, U2 is equal to the internal energy at the second temperature, 1050 R, and this internal energy is 181.48. Again, that's kilojoules per kg. So now we have our initial and final internal energies and our initial and final temperatures. So if we go back to our energy balance equation, we can find the heat transfer, Q in, and this is the mass of air, 10 pounds into 181.48 minus 89.48. We change in internal energy per unit mass, and that's kilojoule per kg. Actually, not kilojoule per kg. We're not working in SI units. We're working in American units. So this is actually BTU per pound. And this is also BTU per pound. And so this change in energy is BTU per pound mass. And so we get the heat transfer. If we perform this calculation, the heat transfer in this process to be 920 BTU.